everyone, my name is Raíssa Silva. Today I will present the work Adaptive Sensorless Model Predictive Control for Permanent Magnet Synchronous Machines. And this research is motivated by Electric Propulsion System for eVTOL, which stands for Electric Vertical Takeoff and Landing Aircraft. And it explores more model predictive control combined with a sensorless observer and online parameter compensation. So in this paper, we investigate the use of model predictive control, or MPC, to drive a permanent magnet synchronous motor under the high load demands typical of eVTOL takeoff. We employ a sensorless observer based on the EKF to eliminate mechanical sensors, and we also propose an online resistance estimation strategy to address the temperature-dependent parameter variation. And the simulation results show that the method achieves a fast dynamic response, accurate torque tracking, and robust performance under changes in load, speed, and temperature. Currently, more than 250 companies are developing eVTOL aircraft, and these vehicles typically use distributed electric propulsion with multiple permanent magnet synchronous motors due to their high power density, high efficiency, ease of control, and an application that demands high torque and reduced acoustic noise. So all of these characteristics are essential for safe and efficient flight. And motor control in eVTOL aircraft presents very strict requirements such as fast dynamic response, safety and redundancy, lightweight electronics, robustness to parameter changes, and hardware cost. And with this, sine wave controllers and advanced techniques like vector control are preferred for noise and performance optimization. Also, a precise rudder position is required for PMSM operation, and a key decision is whether to use a physical encoder or a sensorless technique. And sensorless operation reduces weight, complexity, costs, and points of failure, what is crucial in aircraft systems. And although field-oriented control is widely used, MPC emerges as a promising candidate because it can inherently handle system objectives and transient conditions better. So this article combines three key elements. First, finite control set model predictive control. Second, AKF-based sensorless observer. And third, online stator resistance compensation for thermal variations. Regarding the system model and the eVTOL load requirements, to properly evaluate the controller performance, we used as a reference this flight mission profile. And during cruise, the power demand is about half of the demand during hover or takeoff. So takeoff is the most demanding phase with high torque and power peaks. Therefore, this case study simulation focuses on the takeoff segment, representing maximum operational stress on the propulsion motor. And during the takeoff, the load T varies quadratically with respect to the speed, depending on the lift coefficient CL, the wing area A, the air density, and half the square of the speed. Regarding the permanent magnet machine model, the MPC requires an accurate discrete time model of the motor, and we use Euler discretization to predict the static currents at the next sampling step. And the model includes resistance, inductance, permanent magnet flux, and rotor electrical speed. And because the MPC performance strongly depends on the model accuracy, parameter drift, especially resistance, due to temperature, can degrade performance, which motivates the adaptive strategy. So We have also implemented an extended Kalman filter to estimate the stator currents in the alpha beta frame, the rotor speed, the rotor position, and the load torque. And the observer uses a discrete PMSM model directly in the stationary reference frame, which improves robustness to initial rotor position uncertainty. And the EKF is tuned through Q&R matrices to guarantee fast convergency and stability, and these are defined based on empirical values. So the EKF algorithm follows 4 stages. First, the definition, where we compute the Jacobian for linearization. Second, the initialization, where we initialize the state and covariance. Third, the time update, where we perform the prediction step. And fourth, the measurement update, where we apply measurement correction using the Kalman gain. So with this procedure, the controller estimates position and speed without a mechanical sensor, even under noise and load variation. The finite control set MPC algorithm works in 4 main steps. The first is the input of the motor currents. The control process begins with the real-time measurement and estimation of the motor currents, which serve as the initial state variables required for the predictive model. Second, the prediction of the currents for the next period. So using a discrete time mathematical model of the PMSM, the controller predicts the behavior of the stator currents for the upcoming sampling interval. Third, choose optimal prediction value and its corresponding voltage vector. So for each predictive current trajectory, the controller evaluates a predefined cost function, which quantifies the deviation from the desired control objectives and the voltage vector that yields the minimum cost. So here C represents the cost function with the reference and the predicted currents. And the fourth is the determination of the switching state. So the switching state corresponding to the optimal voltage vector is determined and applied to the inverter for the next sampling period. So regarding online parameter compensation, the stator resistance increases significantly with temperature, and this affects the EKF and the MPC prediction models, causing estimation and control errors. So in eVTOL systems, lighting temperatures already monitored for safety, and we use that measurements and updates the stator resistance online using the linear temperature resistance relationship. And this adaptive mechanism improves the accuracy and robustness in real flight conditions. So here we can see the block diagram of this system, where the EKF observer estimates the speed and position. A PI speed controller generates a torque producing current reference. The FCS MPC directly computes the optimal inverter switching states, and the stator temperature is measured and used for online update of resistance values. So on the simulation, we incorporated a PMSM into a variable frequency drive system featuring the EKF sensorless speed position determination, the PI speed controller, and the MPC algorithm. And the PI controller gains are KP44.2478 and KI 0.1408, and the inverter switching frequency is 20 kilohertz. And here we have also the motor parameters. We are using a 5 kilowatt motor, 500 RPM, 72 volts, 32 poles. So moving to the simulation results, this plot shows the operation at 25 initial winding temperature degrees Celsius, and the system tracks the speed and position references accurately with this temperature. And here on the left plot, we see the reference and the rotor speeds of the MPC scheme under a starting winding temperature of 25 degrees Celsius. And on the top right plot, we initialize the machine at 100 degrees Celsius without parameter compensation. And in this case, we see that the stator resistance increases significantly and the AKF model becomes inaccurate. So as a result, the speed estimation error rises above 1 radian per second, demonstrating the negative effect of the thermal drift. And on the bottom right graph, we see the resistance compensation improves the estimated speed compared to the actual speed. So with the online resistance compensation, the speed tracking error drops from 1.13 radians per second to 0.38 radians per second. And this shows that adapting model parameters to temperature greatly improves the controller accuracy, which is especially relevant for aviation scenarios with repeated takeoff cycles and thermal stresses. To conclude, we have proposed a sensorless MPC strategy with AKF and thermal resistance compensation. The observer exhibited a high accuracy across transient and thermal scenarios. The online parameter adaptation reduced the speed error by approximately 66%. So this approach strengthens the reliability for eVTOL propulsion drives operating in thermally dynamic environments. And future work includes incorporating temperature-dependent flux variation and real-time hardware implementation. So these are our references, and thank you very much for your attention.